now the proof of the theorem. Well, you can guess the proof. So which theorem? The theorem that says that there is a Jordan basis for a complex finite dimensional space and an operator on that space. And a Jordan basis is a basis that make the matrix of the operator look like this. So eigenvalues on the diagonal and blocks that have all the same eigenvalue. So inside each block the eigenvalue is the same. Different blocks can have the same eigenvalue, such as these two here, and ones just above the diagonal on each of these blocks. So this is the theorem. Theorem says there exists such a basis. The proposition says this is true for nilpotent operators. So now, how do we prove the theorem? Well, we know, that's now how we gather everything we knew before. We know that V is the direct sum of generalized eigenspaces. Okay? It's the direct sum of generalized eigenspaces, which means we can split our vector space into these little parts. These parts together don't give the whole space. Of course, we have to add them, not take their union to get the whole space. Yeah? So we take some very small space here, some very small space here. When we add them, then we get everything that all the linear combinations of them. This gives V. And this is the generalized eigenspace. By definition, it is this kernel here. And we know that it's invariant under T. So we can restrict T to this eigenspace, generalized eigenspace. And when you restrict it to G, then we can think of this restriction as an operator going from G to G. So it's an operator on a finite dimensional vector space. Okay. Moreover, if we define Nj, so here for the space J, here we take some J. Yeah, this goes from 1 to N. So fix some J here in the middle. And then we define this operator Nj as the restriction of T to this subspace minus lambda j. What's lambda j? Well, that lambda j would be the eigenvector that we have here. Minus lambda j times the identity. What identity? The identity of this subspace as well. Okay. So this Nj is also an operator on this generalized eigenspace, and by definition, this Nj is nilpotent, right? Because we defined in a way that the kernel of this is exactly this inside here is Nj, and this kernel by definition is the whole space. So which means Nj to that power is 0. So it is nilpotent. And because it's nilpotent, now we can come back here and use the previous proposition, which was done on purpose for nilpotent operators. So we can find Bj a Jordan basis. What's a Jordan basis for this operator Nj? Where is Nj defined? Nj is defined here. So it's a basis for this space. And it's Jordan with respect to this Nj. Which means when we write Nj on that basis, Nj with respect to this basis Bj, this will be the Jordan thing. It has ones here, zeros on the main diagonal, and zeros everywhere else. N by n. Not n by n. K by k. Depends. It's the dimension of that generalized eigenspace. So Nj is the Jordan, has the Jordan form. And if we want to describe now Tj instead of Nj, what is Tj? Well, you just have to add lambda times the identity. So we get these lambdas back here in the diagonal. So we see that this is in Jordan form. Okay? So again, T restricted to this subspace, which is invariant. So vectors in this subspace, when we take T, they stay in the subspace. If we take them with respect to this basis Bj, it is like that. It is this. So now what do? We do this for each of these subspaces. we do the same process. We get these bases for each of these generalized eigenspaces, call these bases B1, B2, Bm, so Bm is for this space, B2 is for this space, B1 is for this space. And then we see what will be T with respect to B. And then you think about it, how if you take a vector in B, it will be in one of these blocks. Okay? So it can be in the first block, or it can be in the second block, or it can be in the last block, okay? Or in any block in between. If you take T of that vector, what is it? Well, it is exactly this linear combination of the vectors on the same block. Yeah? You don't need vectors of the other block to express it, because that subspace is invariant. Okay? So what is it saying? It's saying you just put these blocks together like this, and 0 outside. And this will be exactly the matrix T on that basis. Okay? So what did we get? We got a Jordan basis for T. All we had to do was break V into generalized eigenspaces, work on each one separately, find the bases there, and put those bases back together.